Welcome to Brain Vision.
Starting with the energy for a particle in a box and knowing that the ground state energy is 0.300 electron volts, we go ahead and we do the following. So we calculate, to make things simpler, we calculate Planck's constant times the speed of light in electron volts. So we multiply these two constants, we get an answer in joule meters, but then we convert the joules to electron volts, and we get 1.24 times 10 to the minus 6 electron volt meters, and then we convert that to nanometers as well, so that will be an electron volt nanometers. This just makes the calculations a lot easier. So we finally obtain 1,240 electron volt nanometers. Then, knowing that the energy, the ground state energy, is 0.300 electron volts, we can make, using the equation for the particle in a box, the energy for that, we can go ahead and calculate the photon wavelength by dividing hc by the change in energy between particle in a box energy states. And we have 3 squared times the ground state energy minus 1 squared times the ground state energy, because remember, for a particle in a box, the nth energy is equal to n squared times the ground state energy. So we substitute that in and we have the change in energy. And that's just a very simple way to get this calculation done. So we have 9 minus 1, which we factored out the values for n squared because they have the ground state energy value in common. And then we have 1240 divided by 8 times the ground state energy value, which again is 0.300 electron volts. And I'm sorry, I wrote that in the wrong place, but the value we get for the wavelength is 516.7 nanometers, which you can round to 517 nanometers. So continuing with that, then, we see that this is a green photon, a photon of visible light in the green portion of the spectrum. The other transitions that we can get are the following. So you do the same sort of calculation. You have the 1240, and you know that for values of n, you have n squared times the ground state energy. So you still have the 0.3. So you have really 0.300, but we know that we're going to keep 3 significant figures. So this is really 0.300. So the 4-3 transition is from the fourth energy state to the third energy state for the electron in the box, the particle in a box. And we get a wavelength of 590 nanometers, which is yellow-orange light. It's a yellow-orange color. And this is visible light, of course. So we'll label that as 4-3. The other transitions can be listed here, and we'll just get them in turn. So we come to the next transition, and the wavelength for the transition from the fourth state to the second state is 1240 over 4 squared minus 2 squared times 0.3. And you have 344 nanometers, which is ultraviolet, particularly in the UVA band. So there's a particular band of UV known as UVA. And that has shorter wavelengths, relatively shorter wavelengths than UVB or UVC. And then for 4-1, we have 1240 over 4 squared minus 1 times 0.3. And we get, again, ultraviolet. I'm sorry, that should be UVC has shorter wavelengths than UVA. UVA is actually closer to visible light, which UVA ends at 400 nanometers. I had it backwards, but um, UVC is the one that's farthest out and actually more dangerous. Uh, but UVB is right in the middle between UVA and C. Anyway, continuing, 3-2 transition is 1240 over 3 squared minus 2 squared. And you get 827 nanometers, which is near infrared. So this is on the other side of the visible spectrum. And that's somewhat close to visible light. And finally, for the 2-1 transition, which is our last transition, you have 1240 over 2 squared minus 1 times 0.3, and you get 1378 nanometers, which is can still be considered actually in the near infrared, and but a longer wavelength than what we got previously. So there you have it.